Hello everyone and welcome on today's video. My name is Wouter Peer and I'm the founder and main developer of GHEtool Cloud. And in this first video of the new year, we have prepared something big for you, namely variable flow rates. Now, if you've been following us for a while, you know that this has been a long-awaited feature. We talked already about it in the summer of last year. So let's do a little bit of recap on the physics of borefields to really understand why this is such a big step and why it can potentially change the way you design borefields forever. Now, in order to understand why this is a big update, we need to talk about the borehole resistance. Now, if you have not watched our video, it's linked in the description, but basically it encapsulated everything when it comes down to the heat transfer between the fluid and the borehole. So you have two conductive resistances, the conductive resistance in the pipe, from the pipe through the grout to the borehole, but then you have also this convective resistance to transfer the heat from the fluid to your pipe wall. And although all these three resistances have their contribution, there is an important difference, namely that your conductive resistances, they are fixed. They are based on your design, if you use a singular W tube, or what thermal conductivity your grout has, they are fixed and don't change in your simulation period. But this convective resistance, it depends on the Reynolds number, which does change. Now, the Reynolds number, if you recall, tells us something about the fluid regime, whether your fluid is in a laminar or a turbulent flow rate, and this also tells us something about how well it transfers heat. The more turbulent your flow is, the higher the heat transfer and the lower your borehole thermal resistance, and hence also the better your geothermal system will work, the more efficient it will be. Now this Reynolds number, it's a non-dimensional number depending on a couple of factors, and the formula is given on the slides. It depends on your pipe diameter, which is known. It's determined upon the parameters you use to design your borefields. We have the fluid density and the fluid viscosity, and we have the flow velocity. Now, historically, we know this constant, but we also used constant fluid properties. And we talked about this in summer. Historically, we were only interested in the minimum fluid temperatures. 20 years ago, borefields were mostly designed to be used for heat extraction only, for the heating with ground-source heat pumps. So we only cared about this worst-case fluid parameters. So we assumed them to be constant. Now we already changed that in the summer, but the last thing that remained was this flow velocity. That's also not constant. And today we are also going to change that. So we're going to make the Reynolds number totally variable over time, whereby also the borehole resistance will vary from hour to hour or from month to month if you use a monthly simulation to get the most accurate results out of it. Now, just to recap what we did in the summer, there we said, well, our fluid properties are not constant over time. And when you're heating and you're extracting heat, you're around the 0 degrees threshold, let's say. But when you're injecting heat or you're in the mid-season, it's typically higher, 10 to 20 degrees higher. And as you can see on the graph, your fluid properties change so much that your Reynolds number can also vary with up to a factor of 2. And when you're talking about laminar and turbulent, this can really make a difference. As was also illustrated in the example we saw there. So we had a borefield that was designed with a constant fluid properties, with a constant Reynolds number and borehole resistance as a consequence. And what we see, or what we saw, was that our maximum temperature, it exceeded the limits. So basically, we would conclude, yeah, this borefield is not sized correctly. We cannot guarantee that we have enough cooling because we go above our temperature limit. But when we included these variable fluid properties, we already noticed that, yeah, the fluid's viscosity is better when the fluid is warmer, so your Reynolds number is higher, so your heat transfer is also effectively better. So a borefield that was not sized correctly using the old and conservative assumptions was in fact designed correctly. So this already showed that the step we took in summer was an important one, especially when we were dealing with cooling. Now today we're going a step further than that, because we're tackling the other assumption in the Reynolds number. Is the flow rate really constant? Because let us take a look at this hourly demand profile of an office building. And what you can see here that the power fluctuates somewhere between 20 kilowatt, 50 kilowatts and 350 kilowatts for cooling. And you can also see that the demand in cooling and heating is different. So do they really have the same flow rate? And we have 200 kilowatts maximum in heating, 350 in cooling. Is that the same flow rate? And also if you look, it varies also from hour to hour. Now you can clearly see the white lines, which are basically weekend days, where there is no or very low heating demand. Is the flow rate there also the same as on weekdays? What with modulating heat pumps, where also the flow rate modulates? And that's what we're going to tackle today with variable flow rates. Now, in order to understand how we're going to do this, we're going to look at a simple but really important equation in the whole of heat transfer, basically. And that's that the power we can exchange in the fluid, the power in the fluid, it depends on the mass flow rate through the borefield. So the higher the mass flow rate, the more power we can transfer, the more energy we can transfer, multiplied by the specific heat capacity of the fluid, which we know. It's given, we have implemented variable fluid properties, so we have that, multiplied by the temperature difference. And previously, what we did is we assumed the mass flow rate to be constant. And that's the way we've been designing borefields for 20 and sometimes more years. So we assumed the mass flow rate is constant, what means that if our peak temperature drops or increases, that it's the delta T between the inlet and the outlet temperature that changes. But in reality, typically what happens is that it's the other way around. That we say, okay, we will control the flow rate to our borefield such that we have a certain temperature difference across our borefield. Typically, your heat pump demands somewhere between 3 to 5 degrees Celsius across your evaporator. So that's why this is actually a more accurate assumption, let's say. So by setting the temperature delta between the inlet and outlet constant, our flow rate will automatically vary. Now, how does this relate to what we're talking about? So this is a figure of the effective borehole thermal resistance for the first year for an office building. And what we did is we designed it with a variable flow rate and with a constant flow rate, but we made sure that our peak fluid velocity, so the peak flow rate, the highest flow rate, was the same in both cases. Which is exactly why you can see that here in the middle of summer, actually both our borehole resistances are the same. What is very visible also on this figure is that our orange line, which is the constant flow rate, it varies a little bit because we have these variable fluid properties, and when we go from heating to cooling mode, we have different temperatures and it varies a little bit. Now, when you compare this to the variable flow rate, it doesn't vary at all, basically. The variable flow rate is way, way higher. And this, of course, comes from the fact that, if you recall the temperature or the load profile, the peak powers in cooling were way higher. So our flow rate was way higher there than in extraction when we're heating. And this borefield was simulated with a single U probe. And as you can see in cooling, both the effective borehole resistance from our variable and our constant flow rate are close together, because there were both turbulent flows. But then extraction, our flow rate was way higher, and we do not achieve in reality this turbulent flow rate. And when we're using a constant flow rate approach, since the flow rate is unrealistically high during extraction, we overestimated how good the borehole resistance was. And this you can also see on the temperature graph. So here we plotted the fluid temperature for the first year in both the constant and the variable fluid assumption. And you can see that where it is critical, the maximum temperature, they overlap really well. Because here our constant flow rate is close to our flow rate from the variable flow rate option. But when we go to the extraction or to the mid-seasons, we can see that we overestimated the fluid temperature when we use the constant flow rate. Because in reality the flow rate is lower, our heat transfer is a little bit worse, and so our fluid temperatures should also be lower. Now, this we also implemented in GHEtool, of course. So what we did is we said we are going to work with variable flow rates based on constant temperature differences. And we give you the option to enter it for both extraction and injection, because sometimes they have different set points, or you want to have a different delta T across your heat exchanger than you want across your heat pump. And we also give you the option to work with a minimum percentage of flow rate, because if you have a circulation pump, it cannot go down to 1 or 2% of its maximum flow rate. And typically it's between 10 to 30%. And also, if you go to really low flow rates, your flow rate is almost not moving. Your fluid is not moving in your bore field. So this will give you extremely low Reynolds numbers, extremely high borehole resistances, and some strange peaks. So best to keep it between 10 and 30%. Now, the advantage of using this delta T approach for variable flow rates is that it's easier. And you don't have to calculate the flow rate yourself in GHEtool, so it's easier. It's more accurate. As we saw before, our fluid temperatures are no longer overestimated, and let's say it's now way more accurate calculated. And thirdly, we have now tools to do sensitivity analysis. So we can see what the effect is when we set it, the temperature difference set point to 3 or 5 degrees on our heat pump, let's say. Because that will change the flow rate, and that will also change the pressure drop, but also the borehole resistance and basically the whole design. So you have way more tools to actually calculate how your system will behave. Now, the last thing I want to mention is we've talked about this with an hourly profile, but of course it also works with monthly profiles. So this also means that it's available to all users from now on in GHEtool Cloud to increase the accuracy of your borefield designs. Now, before we wrap up this video, let's jump short into GHEtool Cloud and I show you where you can find it. So here we are in GHEtool Cloud. I created a new project and already loaded the hourly load profile for the office, as you can see here. So let's go to our borehole resistance tab. You can see we have updated the estimates, so you have them now both for extraction and injection. And we created a new tab below for the flow rate. So you will see that all your existing projects have their constant flow rate on, because that was the assumption back then. But now we can select constant temperature difference, and we can set a temperature delta in extraction and injection separately. Now, I already run the simulation, so let's go to the results. You see here still our effective borehole resistance in injection and extraction, like we also had with the variable fluid properties. But now, besides these fluid properties, we also have a different flow rate, different pressure drop, and different Reynolds number. Our temperature profile is the same as you're familiar with, some other graphs. And then below we also updated the hydraulic design. So now, because we have different flow rates in extraction and injection, which you can see here, in extraction our maximum flow rate is just short of 11 liters per second, but in injection it's 26.5. Because of course our peak power is higher in cooling than in heating, so this also translates to different results in flow rates. We have different pressure drops, different required pump hours. So this is a really insightful way, besides the thermal aspects, of course, to also play around with your sensitivity, basically, do a sensitivity analysis on the delta T in heating and cooling or in extraction and injection. Because the higher the delta T, the lower the flow rate, and so you can also make sure your borefield is hydraulically ideal. So this is basically as easy as it is, and the extra insight you can get from it. Now, for a monthly profile, if we go to our monthly profile, You can do it as well, so you can use your monthly values. In our results tab, we again have our effective resistances. We have again a monthly profile, and here you can clearly see the difference in extraction flow rate and injection flow rate. So also for monthly simulations, this is totally feasible. So this is everything I wanted to say today. But you can ask yourself, is this the end of the journey? And because now we took away all the constants in the Reynolds number and we made it all variable over time. So basically, given this framework with the borehole resistance, our game is over, and we have played it till the end. But of course, there are another couple of assumptions behind this borehole resistance that we want to get rid of. So stay tuned for that, because an update is coming in the next months that will again bring your borefield design level to the next game. So I hope you found this video interesting. I hope you will try it out and see what extra insights you can get from it, both thermally and hydraulically. Please share this with your friends, family, colleagues, and I'm looking forward to seeing you in our next video. Take care. Bye.